Okay. Ooh. The sun is shining in this room, so it's maybe hard to see. Okay. Hang on a second. Okay, I think that helps somewhat. So, all right. I'm not going to go through all of the problems on this page. Okay, I'm just going to go through a sampling. I think you can figure the rest out, but the first 5 here are on centripetal acceleration. Remember, that's when we're moving in a circular motion. And so we have a constant velocity value. And our velocity is always changing direction, which means we are accelerating, because even though the magnitude's staying the same, the direction is changing. And we have this force that points inward to the center of the circle called centripetal force. And we also have a centripetal acceleration. Okay. And when we calculate centripetal acceleration, it's a little c, is velocity squared divided by radius, where radius is the radius of the circle. Okay. So in this first example, an object moves in a path with a radius of 10 meters. It's moving at 15 meters per second. What's its centripetal acceleration? We have 15 squared divided by 10. 15 is our velocity. We're squaring that. Our radius is 10. And I cannot find my phone. Burp. Okay, so I gotta figure out how to do this without a calculator. Oh my goodness. Nope. Hang on. Okay. So I'm going to use the calculator on this computer if I can find it. There we go. And make it small. Okay, so, oh no. Not what I meant to do. Okay. Alright, so 15 squared is 225, and I divide that by 10, and that gives me 22.5 meters per second per second. So that's my acceleration of my object. And again, it's accelerating because the direction's changing. Okay, it's not because the velocity value is staying the same, but the direction of it's changing. There's a net force keeping it in this circular motion. Okay. And the rest of these are all like the same type question. What's the centripetal acceleration using this equation? So I'm going to let you figure those out. I'm going to go down to the second half of this page, which is Newton's law of universal gravitation. Okay. And this is where we did what we called a factor of change, also called a rule of ones. So Newton's law, this is gravity for big objects like 2 planets or a planet and a moon or a planet and a sun. We've got this constant, which we don't really need to use, mass 1, mass 2. We divide all that by the distance between them squared. Okay. And what we did with this was we did factors of change. Like if one thing changes, what happens to something else? Or if 2 things change, what happens to something else? So, like for example here, mass 1 is tripled. How does the force of gravity change? What we do is we pretend everything equals 1. And we don't have to worry about this constant when we do this, because it's the same regardless of the situation, because it's a constant. So I have mass 1 times mass 2 divided by distance squared. And then I'm going to triple mass 1. So now my force of gravity is 3 times 1 divided by 1 squared. It's going to be 3 times greater if I triple one of the masses. if my distance between the objects is tripled. So again, same starting point, everything's equal to 1. Now distance is 3 times what it was. I'm going to have force of gravity is 1 times 1, because I'm not changing any mass here, so I'm going to leave them both at 1, divided by 3 squared. I have to square that 3. Gives me 1/9. Okay, so the force of gravity is 1/9 of what it was previously, now that my objects are farther apart. Remember, they can't exert as much gravity on each other if they're farther apart. Okay, and there's a few more like that. I'm going to do one more where two things change at the bottom. So here's mass 1 is doubled and distance is doubled. How does force of gravity change? So now m1 is equal to 2, distance is equal to 2. So my force of gravity is going to be 2 times 1, because my other mass did not change, divided by 2 squared. So that gives me 2 over 4, or 1/2. So my force drops by 1/2. Even though one of my masses doubled, the distance between them doubling is enough to drop that force of gravity, because that's a squared on the bottom. Remember, we talked about how we have a direct relationship between force of gravity and mass, but we have an inverse square relationship with distance and force of gravity. And so that makes a big difference. Okay, so I'll let you do the others on that page using the examples I gave.